Hello, so welcome to learning OCaml, le langage programmatique. Sorry, I had to do it. It's just I'm still kind of moved. It's so nice that OCaml. I just like the way they say it, OCaml, because it's the core team is French, so it's kind of. I'm not trying to make fun of if that's the way they pronounce it. I heard Xavier, he said OCaml, and that's somehow so sweet, OCaml, instead of OCaml. You know, this O and then a camel. So it's just fun way. Okay, I'm not trying to make fun of something. So I was kind of thinking, how do you GCD? And there's so many ways that you can do a GCD, so the greatest common divisor. Let's go to Kitty. Le code de OCaml. I'm gonna fire up utop. Utop. Maybe you would say utop instead of utop. So like OCaml. No, OCaml. Okay, almost every program we write. Yeah, so I read. This is the second time I went through this second chapter of John Whittington's book, OCaml, from the very beginning, and running through names and functions. And it requires practice. You know, I could go on actually to the next chapter. But it's just, I feel like I need to practice this more. It's somehow, it requires practice. Write a function which returns true if both of its arguments are non-zero and false. All otherwise, what is the type of your function? So let's check out. Write a function which multiplies a given number by 10. What is its type? It multiplies a given number by 10. That's simple. That should be very simple. What do you mean? Let function which multiplies, well, it's like mult by 10. Mult by 10. Mult by 10 and some x. Let's do an n equals. Well, how would you define it? Well, n times 10, right? And that's it. So then you call it mult by 10 and some number, let's say 5, and we should get 50. We get 50. And the 50 is a type of an int. So what kind of a function is this? Well, I guess from an int to an int. From an int to an int, right? And if we go on show mult by 10, we get a from an int to an int, right? Write a function which multiplies a given number by 10. Let's actually check what would ChatGPT say to that. ChatGPT was really cool. I tried to do the 99 problems in OCaml, but since I don't know learning OCaml step by step, check this out. So this is something that I want to also do. It's great. So I said I'm trying to solve 99 OCaml problems, but I don't know enough OCaml to do that. Can you teach me OCaml by showing me how to solve the first question, but don't tell me the solution yet. Just by using the example, show me like several steps that I can practice until I somehow can understand by myself the solution. Do you see what I'm getting at? So the first question is write a function last a list, a option that returns the last element of a list. And he didn't give me the solution, which is really cool. And he I don't know why I use he, but probably because I see myself as he. ChatGPT, but it takes so long. GPT. I'll use they. So they said, step 1, understand lists in OCaml. So I really like it how he goes. Okay, whatever. Lists are a fundamental data structure in OCaml. So I don't know. I think it would be nice to do at least some of the OCaml 99. Let's check this out. Exercises, the famous 99 problems in OCaml. So we have a statement and a solution. Right. Is this loaded? It is. How's my OBS encoding overloaded? I guess only sometimes when I load stuff. Yeah, I should load everything before I turn on the stream. Oh, I'm recording, yeah. Tail of a list. Next time I'll stream OCaml. Yeah, I'll stream OCaml. This section is inspired by 99 Lisp problems. Okay. Install OCaml. Write a function last a list, a option that returns the last element of a list. And I was checking out also Zodding. Now Zodding has a nice, you might not find the video because the video itself is titled Let's Talk About Functional Programming. And here actually he just right at the start, already at the 5th minute, he's basically doing the 99 problems. I'm not sure which one. Did he finish it? Maybe he didn't. Yeah, so this is kind of also cool.
Essentially allows you to sort of pipe values through a sequence of functions and so on and so forth. I'm so fucking old. I remember OCaml not having this separation. That's how fucking old I am. So, and I remember the times when I was ranting about OCaml not having this separation, right? And how all of the other languages, all of the other cool kids do have it, and I have to implement that operator myself. That's how fucking old I am. So, oh shit.
Okay.
Boomer Zozin, yeah, exactly. Boomer Zozin. Okay, so let's actually write hello world. I think you write it like this. I almost actually wrote hello world and then print end line because I've been programming in Porth too much lately.
Yeah, because you have to put
right,
print
because
end line
I'm
at the
right
beginning.
now I'm actively rewriting Porth in.
So I have to put print. I know that I have to put print end line first and then hello world. Right. So he's basically writing a simple hello world program. Wait a second. Yeah. Hello ML. This hello. Let unit. Yeah. Okay. I'm just kind of showing off.
Itself, and in fact, right, so I think it's already like 1,000 lines of code or something. I don't fucking remember. So let me take a look at the current state of Porth. So I'm gonna fetch the latest shite and take a look at the Porth. Porth.porth. So here's the current state of Porth. As you can see, I already added all of the intrinsics. Adding all of the intrinsics was relatively simple because we already have implementations for them in Python. So I just had to like copy paste them into 4 lines of code.
Okay.
All of the. So you see, we have a from time to time on this channel. I'm gonna give the link to the source code, which is not as cool as OCaml.
Okay.
Okay, so yeah. What I want you to do, I want you to implement hello world.
Yeah.
If I remember correctly, you implement it like this. So you call functions in OCaml without any parentheses. So it's almost like Porth, but the other way around. You see? So in Porth, I would first put the string literal and then the function. In OCaml, I first put the function and then the string literal. So basically, it's pretty much the same thing.
Yeah. Well, it's just nice to see.
Let's see if this thing is going
to see how he does
to work. As far as I know, you can interpret OCaml, right? So let's actually do all of that in the terminal. And let's go.
So let's also solve actually the first one and practice it. Right. So what do I have to do? What do I have to do? So write a function last. So we have to write a last. So we have some sort of list, right? utop. So we will have some sort of list, right? Let's do this. Let's say my list is, and that's what I know. Let's say 1, 2, 3, 4, 5. Like this. I think it's like this. Unbound value my list. All right, yeah. We have to. Does it work? It does work. We have to use let because it's we are going to define it, right? Define it, yeah. Let. So now we have defined a list of 1, 2, 3, 4, 5. There's so many semicolons. I like more the Haskell. What do you do in Haskell? I think it's space or a comma. Maybe a comma. Yeah, okay. Let my list 1, 2, 3, 4, 5. So like my list is this 1, 2, 3, 4, 5. So now we have to do something like a head. Now in Haskell there is something like a head, my list, unbound value, but I think here is list. I saw it list HD my list, and we get a 1. And last is list tail TL my list, and we get a 2, 3, 4, 5. And I guess you can combine it. So if you want to get a 2 now, you do list head, and then I guess you have to open a parentheses and do list TL my list. So this will first go inside. So first we'll get a last from my list, like a tail, and the tail is 2, 3, 4, 5, and then the list head will take the head, which is now 2, which not 1, right? So we first go from inside outside. So we should get a 2. We got a 2. But the question here is write a function last. So we have to implement our own last function. Now I have no idea how to do that. How do you implement it? Well, how do you implement it? Well, it should, you will have a list of sorts, and it should take, let's say we have a list of 2 numbers, of 2 things in a list. It should take out the first, right? The first thing from the list. What would that be? How would you approach this? Okay, let's see what ChatGPT does. Lists are fundamental data structure in OCaml. So I told him to teach me OCaml and not give me the solution. So let's start by using this example. So lists are fundamental data structure in OCaml. Let's start by creating and working with simple lists. Create a list. So I guess you can also put like a comment here, but that makes no sense, right? Comment. Yeah, comment, and that's it, right? You wouldn't like let comment. No, that would be actually silly, right? Comment, syntax error, right? Let comment equals comment. Access the head. Let head equals list HD my list. Yeah, well, that's silly, right? ChatGPT, that's very silly. Let head be what? List head my list. Access the tail, everything except the first element. Let tail equals list tail my list. Practice create lists of different types in string, etc. and try using list head and list tail. What happens with an empty list? Yeah, what happens with an empty list? List HD like this. Exception failure HD. Yes, it fails because except if we do, I think if we do tail, then it fails too. That's an exception. So it's not like a pure function because it fails here. We should define it so that it doesn't fail. I mean, so that it fails gracefully. Recursive functions. We will need recursion, right? Recursive. Les fonctions récursives. Sorry. Recursive functions are often used in OCaml to process lists. Try writing a simple recursive function to count the number of elements in a list. Well, yeah, recursions. That's what I was practicing the last thing. Write simple recursive functions like summing the elements of an int list or reversing a list. We could do all these things. So recursive, but it introduces actually pattern matching. Okay, let's do this simpler without pattern matching yet, with conditional statements. What would be the most elementary recursive example we could create? I mean, a question, a baby-like 99 problem for someone not feeling yet so intuitively with recursive evaluation. So sum the numbers in a list. Yeah, that's probably a basic example, right? So write a function. Sum is a type of an int, list int, that calculates the sum of all numbers in a list. If the list is empty, the sum should be 0. So we have a base case. So think about the base case. What happens if the list is empty? Well, if it how do we do that? Write a function sumList. SumList. We have a sum. Show sum unknown element. So we don't have a sum. Okay, we can use that. Let sum equals what? Well, sum of what? Of something in a list. So let's sum of a list. Can we call it a list? Let's sum LST equals. How would you do it? Well, a list would have members, right, of the list. How many? How do we sum them? Well, we sum the first one with the rest. So you could say like member like N1. Let's call it N1. But sum list. You see, let's sum. How would you sum a list? Can I use LST for? Yes, I could name my list LST. So let's sum list. Well, yeah, I need to sum the first with the rest. You could say like that, right? Let's sum list. Okay, but we also have to do if LST is empty. How do you say if it's empty? Oh yeah, if the list is empty, the sum should be 0. Well, that's the base case. That's also one thing with recursions. The base case is also the exception, I guess. Or like, the thing if it fails is also the base case, which is kind of nice. Think about the base case. What happens if the list is empty? Because we will sum all the numbers, and when we are left with 0, that will be the base case. That's how the recursion will stop. So what happens if the list is empty? The sum of an empty list is 0, so the base case will return 0. But how do I write the base case? Let's sum list. If list equals... If list is empty, well, can I do it like... Maybe I know far too little. If LST equals empty list, then maybe we could check if... How do we write... Wait. Let's first implement a function that checks if the list is empty or not. Right? So I give it a list with members, and it tells me, and it gives me a Boolean value true if it's non-empty list, and false if it's empty. So write a function is empty, a list bool that takes a list and returns true if the list is empty, and false if the list has at least one element is empty. So let's start is empty LST equals, if LST equals, I think it's this, then false, else true. So this is val is empty. So what kind of a function did we just write? At least it worked. Is empty. Val is empty. Is empty. What does it say from a bool? A list. We have an a ampersand. Why is there an ampersand? So write a function is empty. Why ampersand? That takes a list and returns true if the list is empty, and false if the list has at least one element. We can use a simple conditional statement. If the list is empty, return true. Otherwise, return false. Oh, I said return false. If the list is empty, then false. Wait, let's try it actually. Is empty, and let's give it an empty list. It says false. Oh, this is the wrong way how I did it. I should say true. Yes, list is empty, not false. It's almost like the computer is looking at me and saying true, because I'm saying, is it empty? And the computer should say, yes, true, is empty, and not false. So it's not defined well. So let's do it again. Let's empty LST equals. So if LST equals empty, then true. You see, but it might be confusing, right? If LST empty, then true. So if LST is true, if LST equals empty is true, then true, it is empty. Else, false. So now we have an A-list bool fun. Right, let's try now. Is empty, LST. Let's try an empty list. True. And let's do is empty. Do 1, 2, 3, 4, 5. And false. It's not empty. Okay, we have a beginning. So what did we say? Okay, step-by-step solution. Let's see how he did it. Let is empty LST. If LST equals, then true, else false. Great. Should return true. Okay, manual evaluation. Let's see how is empty 1, 2, 3 evaluates. The condition LST empty list checks if 1, 2, 3 is equal to empty. But it's interesting, if you give it, it's just something which I think, yeah, I wouldn't think at first. If I check is empty 1, 2, 3, 4, 5, it does check this, right? Oh, so if I give it 1, 2, 3, 4, 5, it will do if list 1, 2, 3, 4, 5 is equal to empty, then true. So it checks this, actually. This thing computes, but it's not true because we have 1, 2, 3, 4, we have 5 things in a list, or 5 members, or I don't know, 5 elements of a list. So this is not equal, right? Is empty equals, right, is empty, because we could try 1, 2, 3, 4, 5 equals this, right? We get a false, right? And if I do, we get a false, right? Then true. But the first part of the if checks for the truth value, for the true value. And then since this is false, it goes to the second branch, else false. It just may be confusing because you say false and then else false, because that's what it will say, actually, false, because it's false. Okay. Maybe I will. Yeah, this took a while. So let's see how is empty 1, 2, 3. Next step. Once this works out, you can use is empty in larger functions, like checking if the list is empty before trying to access its elements. Let me know if you're ready for that. Well, what did we begin with, actually? To summing up, to sum the list. Well, we want to sum the elements of a list, right? So we do have the empty now. The is empty function that checks if the list is empty. We can use that as our base case. If empty, can we? But since it returns a boolean, but how will we sum it then? We need a recursive call. Let's sum list. Yeah, I can already see it. I know that it's funny. I see that the body of the function, so the inside body of it, will have a recursive call such as sum n number, right, which is the first element of the list. So the first n will be added or summed with the rest of the list. But the recursive call will be something like n plus sum of the rest of the list. But what's confusing to me now is that while I am defining the name of this function, such as let sum lst equals body of the function, how would I call then the n or some n number inside of the function? Do you see what I'm getting at? Don't tell me the solution. It's funny, it's something where I'm stuck. I see exactly what you're getting at. You're grappling with how the function knows about the first element of the list and how to refer to the rest of the list inside the recursive function. This is critical insight and a fantastic question. Thank you. Let's break it down into steps without giving away the full solution yet. I like this. Edging with ChatGPT, right? Is that the term? Defining the function. Yeah, let sum LST. When you define the function let sum LST, you're saying I'm giving this function a name sum, and it will take a parameter LST that represents a list. We do get that, but inside the function, LST is the whole list you passed in, but now you need a way to refer to the first element called n or x, and the rest of the list, often called x's or tail. Now, getting the first and the rest without pattern matching yet. Without pattern matching, you can use LST head LST to get the first the first element. Oh, that's too soon then. Wow. You're right. We would use a head to get the first. Let sum LST equals. So we'll use list HD. So list head would be but list head of what? List head H head of yeah, I don't like the H list head. Wait, I'll just rename it. Let head equals list AD. Can I do this? And let tail equals list tail. All right, great. Okay, so let sum LST equals head of the list times, no, plus head of the list plus the sum. Yes, because if I do head of the list plus what? The tail of the list? But I cannot sum these things, right? I cannot sum the rest of the list. I have to separate them, right? I can't do tail. It won't work like this. It will work. It will work. No, it won't work. Expression has type int list, but an expression was expected of type int. Yeah, you see, the expression has type int. Yeah, I'm trying to make like the example where I let sum LST equals head LST plus head LST sum LST. It's fascinating how I still don't get this, and I'm making a video of it. So I have to add the first thing in the list, right? You have 5 things. I add the first thing, and then I have to start again. That's the trick with the recursion. I take the first thing, I add that to what? And then again take the first thing and then I add it to what? I take the first thing and I add it to what? So it's almost like the head of the list. Look at this. Okay, my list. Do I still have this thing? My list? 1, 2, 3, 4, 5. So how do we, let's do this actually. I'll do this manually. So head of my list plus head of a tail of my list, right? Let's make a short list actually, because this is too long. My list 2 equals 1 and 2. Did you mean my list 2 unbound value? No. Okay. So now we have a my list 2 with 1 and 2. So now I will do head my list 2 plus, can I do like tail? Head of a tail. No, I have to do actually head of a tail. My list 2. And that's a 3. That's a 3. So the head of a list plus the head of a tail of the list. So it's almost like the first thing I add to the first thing of the rest of the rest of the list. And the rest of the list is 2, 3, 4, 5. And the first thing of the rest of the list is 2. So 1 plus 2 plus head of the rest of the list. And the head of the rest of the list is 3, 4, 5. And the head is 3, so 1 plus 2. So you like, you add the heads of the rest of the list. So that's how you would sum a list. But the 99 OCaml asks to implement a head. Let first is list. Yeah, that's what we did. Now you can talk about first. First sum rest. Yes, but that's what I thought first. So let sum of LST equals head plus sum tail. But this won't work. If I do plus sum tail, right? It won't work. Because why it won't work? Sum of the list equals head plus, so head of what? Let sum LST equals head of LST plus sum of the, it's that recursive evaluation circle that I'm again missing. Sum of the tail of the list. Sum LST tail list. You see, this is not. Let sum LST equals head of the list, which would be, let's say, 1 plus. Now I need to somehow automate that thing, what we did before manually. How do I do that? Well, I need to reuse the sum. Head list plus sum of the list. Right. This is wrong, but let's do this. If this is a recursive definition, you should add the rec keyword on line 1. Thank you, compiler or interpreter. Let rec sum lst. So let rec sum lst equals head of the list plus, and you add the rest of the list. Now it's not good because we have to implement it. So we're just saying add it with the rest, but how do you add the rest? This is not working, right? So sum 1, 2, 3, 4. And look at it. Stack overflow during evaluation. Why? I expected this. Because head of the list plus sum list, what happened? It doesn't end. It doesn't end. Yes, just plus sum of the list, head of the list, plus sum of the list, head of the list, plus sum of the list. And then it does again, head of the list plus, so it never stops. Let rec sum of the list. Let rec sum of the list equals head list. Head of the list plus sum list. Fascinating. I'm doing this for 40 minutes. Let rec sum list equals head sum list plus sum list. Head of the list plus sum of the what? Of the head of the rest of the list. Yeah, but how do you do that? So head of the list plus sum fascinating. Head of the list, let's say that's 1 plus sum of what? How would you sum it? You can't just add sum of the rest. Well, sum, it's the function. Sum of what? Maybe I should put this, yeah, I have to put it in parentheses and then tail of the list. Now this is head of the list plus sum of the tail of the list, head of the tail of the list. Head of the list plus sum. Wow, I feel so dumb. Head of the list plus sum of the tail of the list. Yeah, this will also not work. Because if we do it 1, 2, 3, 4, failure, you see, exception, failure. Sum of the list. Let's see. So now you can talk about first and the rest of the list. This will allow you to add the first number to the recursive call on the rest. Once you have the first and rest, the recursive call would look like this. First plus sum of the rest. Yes, but we need to define the rest. Notice how the function calls itself on the smaller list, rest. So the rest is the smaller list, that's true. So this keeps shrinking the list until eventually you hit the base case where list is empty. So if is empty true, if is empty is true, then what do? Then true. Else, well, it should write false then, right? Let sum of the list equals, if lst is empty, then false. Else else. Notice the function using isEmpty as the base case. You can use isEmpty function as a condition. If isEmptyList is true, return 0, the base case. But we need to, that's what this they are, we need to, and 0, not false. We need a base case because we want to sum the list. I missed that part. If list is empty, then 0. Else. Otherwise, compute first plus sum of the rest. This links back to your observation that recursion peels off one element at the time. How do I name the first element and the rest of the list inside the function? But this wouldn't work, else head first plus sum rest. Else head plus head of the list plus sum, else head plus sum of the tail. I don't think this will work. This expression has type a list, but an expression was expected of type int. What you can try now, inside sum, write something like this. First list, rest list. Try printing first and rest to understand what they represent. Think about how the recursive call would look. First plus sum rest. Combine is with empty to handle the base case. You're very close. Yeah, but it's the same definition. Sum list. Else head of the list plus fascinating, because we are using sum, but sum isn't really defined. What is sum? What is sum? I'm using the sum, but it's like I'm not defining it. And for 40 minutes already, I'm thinking how to sum the rest of the list without stack overflow. It's like I see it's the head plus the head of the rest, and then again plus the head of the rest. But I need to make it a recursive call so that I can input however many elements of the list I want. You're right at the heart of recursive thinking, and it can feel a bit like untangling a knot at first. Let me help you step through this carefully so you can see how to define the recursive function properly without causing stack overflow. The thing, it's weird, like I could implement this one day and the second day it's poof, gone. So breaking down recursion, base case. So this is the condition that stops the recursion. If you don't define this, the recursion will keep going forever, resulting in a stack overflow. For summing a list, the base case happens when the list is empty. The sum of an empty list is 0, so it will not be a false. Now the recursive case, this is where the function calls itself on a smaller piece of the input, the rest of the list. To avoid stack overflow, the function must always move closer to the base case. Right, we gotta get closer to the base case. For lists, this means the list must get smaller with each step. So the list does get smaller. That's the contraction or the expansion. I guess it has to expand, right? Okay. Wait, how do I open up a new like this? So check this out. Wait, sum. So we have 1 plus sum. No. We have sum. Let's do 1, 2, 3, 4, 5. 5. Okay, so we have 1 plus sum 2, 3, 4, 5. 1 plus 2 plus sum 3, 4, 5. 1 plus 2 plus 3 plus sum 4, 5. 1 plus 2 plus 3 plus 4 plus sum 5, right? Or is it still actually still like this? 1 plus 2 plus 3 plus 4 plus 5 plus sum, it's still going on, empty. And now the base case is here, 1 plus 2 plus 3 plus 4 plus 5 plus sum, and if it's an empty list, then 0, we said, 0. And now we add them all up. So we could do 1 plus 2 plus 3 plus 4 plus 5. 1 plus 2 plus 3 plus 4, actually that's 9. 1 plus 2 plus 11, oh no, 12. 1 plus 14 and 15. Right. So that's the kind of the space-time complexity, I guess. But this is what I have to write. And I can't write it. So what's going on? I have a head plus sum of the rest. And then I have head plus wait a second, if I just look at this, well, then it should be like this actually. Head of the list plus sum of the list. So you realize the sum is the first. Like, yeah. Copy this. Like, I can write this out, but I still cannot implement an algorithm or recursive call to do this. You're really close to cracking this. Let me help you organize your thoughts and translate your breakdown into a working recursive function step by step. You're already understanding the recursive process, but it's just about connecting the steps into the code. Your manual process. Here what you're doing manually. You start with the first element and add it to the sum of the rest of the list. But break the rest of the list into smaller parts, summing one element at a time until you reach an empty list. Add everything together as the recursion unwinds. This is exactly how recursion works programmatically. Let's convert your steps into code. Define the base case. The base case is when the list is empty. You correctly wrote if is empty lst then 0. This ensures that when there are no more elements, the recursion stops and the function returns 0. Now get the first element and rest of the list. Get the first element and the rest of the list. To sum the list recursively, you need the first element. Wait. This one was, wait a second, nostalgic. This one was a bit slower. Alright. It was too much. Get the first element and rest of the list. To sum the list recursively, you need the first element and the rest. Right. So first rest, right. Recursive call, right, we know this. Once you have the first element and the rest of the list, the sum is first plus sum rest. Combine base and recursive cases. Put it all together inside the function. So let rec sum lst, right. Let sum lst. Oh, I didn't do this rec thing. Like rec sum lst. If lst is empty, then 0. Else head plus sum of the list. Head plus sum of the rest. Sum tail. Sum of the tail. Tail of the list. No. Put it all together inside the function. So if is empty lst, then 0 base case. Else lst, you just wrote it. Wait a second. The head of the list plus sum of the tail of the list. But plus sum of the tail of the list. But head of the list also. So this would work. The expression has type a list bool, but an expression was expected of type b list. Oh. Did I define is empty? Let's define is empty again. Let is empty lst equals, if lst equals to this, then 0, else false. The expression is type bool, but an expression was expected of type int. Yeah. If is empty lst, then 0. So you mean I can just have the then case? The then branch? It's fascinating how much time this takes. Wait a second. Let rec sum. I think I can go into second line equals, yeah, like this. Okay, let rec sum list. If lst equals this, then 1. Like this, right? Else head of the lst plus sum of the tail of the lst. And now we have our list. Sum of the 1, 2, 3, 4. 11. 1 plus 2 is 3 plus 3 is 6 plus 4 is 10. What? Oh, because we did, okay. This thing is wrong. So if lst is empty, then 1. No, then 0. That's why we got 11 instead of 10. Now it will work. Sum lst 1, 2, 3, 4. The function has type int. List int is applied to too many arguments. Some LST. So many mistakes. Yeah, some LST in the list. No. LST is the list in the definition, but I don't write it now. Just do 1, 2, 3, 4, 5. Let's do 6, 7, 8, 9. I think Caml has this thing also. 10, which is nice. Syntax error. It doesn't. Oh, that's too bad. You have this in Haskell. How do you do in OCaml something like list init generates a list by applying a function to each number in a array. To create a list, oh, you have to do this. Maybe like this, sum 1, 3 dots, and then 10, like this. Highlighted. It's not so pretty, this. Let's do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 45. So now it works actually. But why does it work? It's funny. Why does it work? The head of the list. What's the head of the list is 1. And then we plus what? The sum of the tail. If we only had the tail of the list, we wouldn't get anything. We would just get a list. But we have to do the sum. Oh, the sum, and then we repeat the entire thing again. So this is the so this part, sum of the list, is what kind of moves around. Let me print this. Oh, look at this screen. Like this, yeah, I'll do it again. Okay. So sum of the list plus sum is like this sum tail list. The whole thing, it's this, right? The sum of the tail of the list is this same function doing it again. And I think mentally we somehow are still within this first iteration. And I do head of the list plus, and I cannot make this mental leap and do it again. So summing, it's almost like I want to have some kind of operator between sum and the rest. It's almost like, how can sum do anything? But sum is the name of the operation that I'm doing. I'm summing it, but what am I? I'm taking the head and I'm summing it. Will add it to what? To the sum of the rest of the list. And what is the sum of the rest of the list, right? What is the sum of the rest of the list? Right. Yeah, fascinating. So let rec of the sum of the list. If list is empty, then 0. Else what? Else head of the list plus sum of the tail of the list. Okay. I got it now. But it's that mental leap that when I see the part that says sum of the tail of the list, I seem to be stuck within the same evaluation, within the same part of the evaluation, and I didn't go back to the definition, which is sum of the list, now being defined or starting from the tail of the original list. Do you see my mental hiccup? Your insight. Yeah, I see your mental hiccup clearly. It's a common and important learning step when working with recursion. Let's untangle this together. So your insight, when you write sum of the list, it feels like you're stuck in an endless loop of evaluating the tail of the list without zooming out to recognize that you're applying the same function definition sum to a smaller piece of the problem. This is where recursion can feel tricky. You need to trust, I need to trust that each recursive call is its own instance of the function. Okay, that's the part. So each recursive call is its own instance of the function with its own input and evaluation. So let's make this mental leap more concrete. A recursive function works like this. So each call to the function creates a new instance of that function. Each call to the function creates a new instance. So this means when sum is called on a tail of the list, it doesn't know it's part of a bigger problem yet. It's just solving the problem for the smaller list. That's also interesting. So these calls stack up until the base case is reached, and the base case returns a result. And each previous call adds to that result as the stack unwinds. That's what we did here. So when sum is called on the tail of the list, it doesn't know it's part of a bigger problem yet. Look at this, tail, 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 and then stack up until the base case is reached. So this is the expansion, right? And the base case returns a result. This is here. The base case now returns a result, which is a 0. Finally, so that's actually the first result. Here we're not actually making a result, we're just kind of extracting the head of the list, and then the head of the rest of the list, ahead of the rest of the list. So the base case returns a result, and each previous call adds to that result as the stack unwinds. Breaking the hiccup with an analogy. Think of recursion like peeling layers of an onion. Each layer is one recursive call, and the base case is the center of the onion. You peel one layer at a time, sum, tail of the list, until there's nothing left to peel. Sum, tail of the list, sum, tail of the list, sum, tail of the list. And then as you build up, unwinding, you add each layer back, the head of the list. You add each layer back on. Why would I add each layer? You don't need to think about all the layers at once, just focus on peeling one at a time and trust that the base case stops the process. Yeah, why would I add the onion layers? Now he's doing the visualization. What we did, 1 plus sum 2, 3, 4, second call. The head is 2 and the tail is 3, 4, 5. So it becomes 2 plus, okay, this is nice. So the first call is, okay, sum of the list, the head of the list is 1, and the tail of the list is 2, 3, 4, 5. So this becomes 1 plus sum of the rest of the list, or sum of the tail of the list. Second call, sum of the rest. Now we have sum. So this is now the second call. Oh, this is actually interesting. I also skipped this. When we do head of the list, which is, let's say, 1 plus sum of the rest of the list, when we are doing now summing of the list, this is that tail. Let's say 2, 3, 4, 5, starting from 2. And now sum of this thing, and the head is 2 plus sum of the rest. Yeah. Those are how it unwinds. This is the resolving. Oh, this is also interesting. Sum 5. 5 plus 0 is 5, because that's the base case already. Sum 4, 5, 4 plus 5 equals 9. I guess you would have to write also plus 0. Why the hiccup actually happens? You're focused on the middle of the recursion without zooming out to see each recursive call is solving a smaller problem. Once the smallest problem is solved, everything else resolves automatically. Each recursive call is independent, solving for its input list. The definition of sum is always the same, no matter the input size. Mental model to overcome it. Here's a way to train yourself to zoom out. Think of each recursive call as a worker solving a smaller piece of the problem. Trust the worker to solve its piece and return a result. But I think the thing is because it's the same worker. Your job is only to add the result from this worker to the head of the current list. It helps, but to me it's more like each worker is that same worker, isn't it? It feels like each recursive call is the same worker rather than different. That's a fascinating perspective. It's actually both true and not true. It's same, but in different states. Each recursive call reuses the same function definition. Maybe I'm thinking too imperatively, so it feels like the same worker. However, each call is working on a different input, a smaller version of the list. So in a way, it's like the same worker performing different tasks sequentially. Here's how to think about it. Imagine a worker, the sum, who takes a list as input, processes the first item head, and leaves the rest for themselves to handle next. The worker does not repeatedly. The worker does this repeatedly, but they leave a note for their future self. Once you figure out the sum of the smaller list, add it to this head. When the worker finally gets an empty list, they stop and say the sum of nothing is 0. Then they work their way backwards through their notes. Oh, now I know the sum of the smallest list, so I can complete the sum of the slightly larger list I was working on before. The worker's stack of tasks. Here's how the worker keeps track of tasks, their notes. Start with sum 1, 2, 3, 4, 5. The worker processes 1 and tells their future self. When you finish summing 2, 3, 4, 5, add 1 to that result. That's kind of the same. This is a similar example what Sussman did in science, in structure and in interpretation of computer programs. He uses that with people who it's the same thing. And he actually compared this kind of computational thing with bureaucracy, but also it was so cool. He was comparing that because you keep all the data somehow. You can always at each step of the computation, you know where you are. Hey. Okay. Neka samo je gotov, sad još malo. Alright. This will be it for this time.